Okay, welcome back everyone. In this video we're going to talk about total internal reflection. So we've been talking about Snell's law and refraction, and it turns out that there's times that it doesn't work so well. So usually what happens is if we have a dense medium like water or glass, so we'll call that N2, and a less dense medium, so that N2 is greater than N1, sometimes we have a case where we have an incoming ray that is actually coming in at too shallow an angle measured from the boundary, or too great an angle measured from the normal. So just to toss some numbers onto this, maybe 1.5 and 1, and maybe this is 70 degrees is theta incident. So we know that if we go from more dense to less dense, that the ray will actually bend away from the normal, like so. Excuse my poor drawing skills. And we know that it's going to follow Snell's law. So we could say that N2, let's call that a 2, sine of theta 2 equals N1 sine of theta 1. Now, we're going to run into a problem here because we have 1.5 and then the sine of 70 is equal to 1 times the sine of theta 1. And theta 1 is what we're trying to find, the so-called refracted angle. And we're going to break out the calculator here and do a little bit of quick math. So it turns out that if we take 1.5 times the sine of 70, we're going to get 1.41, and that's going to equal 1 times the sine of theta 1. So in order to undo this to get theta 1 by itself, we have to do the inverse sine of 1.41, and when we do that, at least on my calculator, it says error. That's never good. So what's going on? Well, it turns out that if you have a ray of light which is in a dense medium trying to escape, and it's coming in at too shallow an angle, it won't escape. The math just doesn't allow it. And what happens is total internal reflection. So in this diagram you can see here's a light source, so light's going out at all sorts of different directions, and of course if it goes perpendicular to the surface, it's not refracted at all. Okay, it just goes straight through. And if it's at a small angle, okay, to the normal, it will be partially reflected and partially refracted. And you can look up the coefficients that this diagram talks about, and that just depends on the materials. But eventually you get to this angle theta c, the critical angle. And at this angle, the refracted ray kind of travels along the boundary. So what you can see is that this refracted ray is slowly bending over and over and over, and finally it's going along the boundary. So it's not really escaping. It's traveling along the surface. Okay? And this happens when you have light striking a medium with a lower index of refraction. Now, when it has an angle that's larger than the critical angle, so if theta incident is greater than theta critical, it's total internal reflection. And this has some very important uses. For example, fiber optics. Okay? Fiber optics is simply sending light down a cable and letting it bounce around. And it looks kind of like this. Okay? As long as you do this correctly, and you have a dense enough material for this cable, no light is ever going to come out the sides. It's only going to come out the ends. Okay? So that's total internal reflection. And it turns out that we can calculate what total internal reflection, or what the critical angle is. So basically, remember that we talked about a so-called critical angle where the refracted ray would basically travel along the surface. And at this point, theta refracted is 90 degrees. So this is N2 and this is N1 and theta 1. So what we can write is that N1 sine of theta 1 is equal to N2 sine of 90 degrees. And in this diagram, this is actually theta critical. So that's what we're looking for. And so if we want to solve for theta critical, we just go like this. So it's N2 over N1. And lo and behold, what's the sine of 90 degrees? It's equal to 1. So we don't put anything there. And this means that the critical angle is going to be the inverse sine of N2 over N1. Now if we go back to our prior example where N2 was 1.5 and N1 was 1, okay, and if I take the inverse sine of that on my calculator, just to see what was the critical angle, it turns out that the critical angle was, hold on one second. Oh, I am doing something very horrible here. I should be doing, excuse me, N2, which is 1, over N1, which is 1.5. So the critical angle, okay, so 1 divided by 1.5, take the inverse sine of that, and actually what that comes out to be for this particular situation is 41.8 degrees. So when I set this up and said it was coming in at 71, I knew that this was set up for failure because I knew that the critical angle was only about 42 degrees. And so what you can see is that the denser the material, the smaller the critical angle is. Okay, so here's another application of this, and that's the diamond. Okay, so guys slash gals, whenever it's time to buy one of these things, you want to pay attention to the way that the diamond is cut. The diamond has to be cut ideally, so that's this diagram right here. And what this means is that any light that strikes the diamond from the top, that enters the diamond, hits the bottom face, becomes totally internally reflected, and emerges from the top. And this is the so-called sparkle that you see with diamonds. So being a physics major, when I proposed to my then girlfriend, I made sure to test each diamond carefully and calculated exactly what cut to have so that I could get the best sparkle on that diamond. So let me move this down a little bit so you can see. You want to make sure that the diamond is not too shallow or too deep. Okay, if it's too deep or too shallow, the light will escape and you won't be taking advantage of total internal reflection. And there's all these angles that you should have, and all sorts of ratios, and it's actually pretty fascinating how much you have to think about total internal reflection. Okay, so that's it for this time. I will catch you next time with an example of total internal reflection.